Hello everyone, my name is Felipe Lopes. I am from the Federal University of Paraíba, Brazil, and I am here to present the paper Adaptive Traveling Wave-Based Algorithm for Time Alignment of Transmission Line Fault Record. Firstly, I would like to point out that this paper was written in partnership with these co-authors, Tiago Norato and Gustavo Cunha from University of Brasilia, Nilo Ribeiro from Eletronorte, Paulo Lima from Schweitzer Engineering Laboratories Brazil, André Coelho and Daniel Becker from State Electricity Generation and Transmission Company GT. This paper is focused on post-event fault studies, and we know that when a fault takes place on a given transmission line, local and remote records are expected to be generated. And if we need to analyze these records simultaneously, they must be aligned in time. And to do so, the GPS and communication channels have been widely used. However, we know that the GPS antennas may fail, the GPS signal can be lost, the communication channel may fail, or it can be out of service, in such a way that in this case, using unsynchronized records in post-fault studies may be a problem, especially if you need a microsecond timescale accuracy. Thus, in order to obtain a time synchronization with microsecond accuracy, in this paper we analyzed traveling waves. Basically, we consider a given bus L as reference, and at the opposite line side, we consider the existence of a bus R, which represents the remote bus, which is the unsynchronized bus in which there is a synchronization error xi. Therefore, when a fault takes place on this line, it can be concluded that the real traveling waves will be measured correctly, considering the correct reference only at bus L. So we can detect here TL1 and TL1R, which stands for the time instant at which the reflection from the fault reached the monitor tab. However, if we consider the bus R measurements, it is easy to perceive that there will exist a time displacement here due to the synchronization error in such a way that the measured traveling waves will be different from the real ones. So our goal here is to compensate this error here, xi. In 2020, we published a paper in which an automated solution for local and remote data time synchronization was presented. Basically, in this paper, we calculate a synchronization term kappa, which is a function of the line travel time tau and of the detection, the arrival times of the fault launched waves which reach the monitored buses at the bus R and bus L. But regarding these time differences here, okay, we can calculate. We have already technologies capable of accurately obtaining these time differences, but we have to recognize that there will always exist uncertainties in the line travel time because the line parameters may vary over the time, and even if you consider a line energization maneuver in order to calculate tau settings, we should know that these uncertainties will still exist. So the goal of this paper is to develop a new formula capable of adapting kappa to uncertainties in transmission line travel time. So to remove tau from the kappa formula, basically we analyze the classical fault location method applied to both line terminals, and we add one equation to another, and by doing so it is possible to obtain an equation that represents the line travel time. This, substituting this equation in the original synchronization equation, we can obtain an adaptive formula which is represented here. This formula can be further simplified, resulting in this one. And if we consider a practical perspective, we must know that these time differences here are indirectly available in single-winded traveling wave-based fault location estimation. Indeed, even if a wrong tau setting is used, a wrong distance fault distance estimation will be obtained, but these errors will be cancelled in this term at the right side here in such a way that the time difference of interest will be accurately determined. Thus, based on this idea, two methodologies are proposed in this paper, and the methodology M1, we consider that the single-winded traveling wave-based fault location estimations are unavailable. In the methodology M2, we consider that these estimations are available. Talking a little bit more about these methodologies, when we consider that the fault distance estimations are unavailable, the user must manually identify traveling waves reflected from the fault point. And to do so, different methodologies can be used, and in this paper, the search field technique is applied, which basically considers a rough phasor-based fault distance estimation, and based on that, we estimate the time instant at which we expect to see the fault reflection, and based on that, we use some margin, and then we compare the polarities of the waves within this search field in such a way that we can detect the reflections from the fault point, and thus that synchronization formula can be further simplified, resulting in this one here. In addition, the methodology M2 considers that the single-winded traveling wave-based fault location functions are available, so the user just have to download the fault distance estimations, and based on these estimations, we obtain this formula for kappa here. So you must know that even if we use wrong tau settings, it's important to point out again that even if we use a wrong setting, these distance estimations will be wrong, but kappa value will be correct. So regarding the results, we started the analysis considering simulated scenarios. In this case, we consider a very realistic implementation of a Brazilian transmission line, which is implemented in the Alternative Transits program. This is a 230 kV 6 Hz system. Is a transmission line 344.16 kilometers long, and to do so, the J-Marty model was used. This is the real line travel time of the system, and to analyze the performance of the proposed solution, the final time synchronization error ES was considered, which consists of the absolute value of the sum between the error sheet and the synchronization term kappa. In these simulations, real traveling wave-based devices were used, and the test consisted of playback simulations directly in the device's memory. And since the simulations returned synchronized data, the synchronization errors were added manually to the remote terminal data. So this is the illustration of one of the analyzed case. This is a BC solid fault case, considering a fault at about 50 kilometers from bus B here. And the error included in the remote side measurements was of about 1.46 seconds. In this case, we intentionally considered an erroneous tau setting. We used 1000 microseconds, so there is a difference in relation to the real value. And as a result, some errors were verified in the fault distance estimations. Here, something about 9 kilometers of error, which is unacceptable for traveling waves methods. But we can see that kappa was very accurate in such a way that the final synchronization error was equal only to 0.253 microsecond. The same analysis was performed for other case, and in all the simulated case, these synchronization errors did not exceed the order of 1 microsecond. So now analyzing real scenarios, firstly we took into account some cases which are originally synchronized, and then we could add some time synchronization errors. By doing so, we have a controlled case in such a way that we calculated kappa and then we compare it with this error, resulting in a final synchronization error equal to only 3.063 microsecond. This is very promising. It's smaller than 5 microseconds, for instance. So just few microseconds were obtained, and it is important to emphasize that this is the worst case presented in this paper. In a second part, in which we evaluate also real scenarios, we took into consideration some records which were originally unsynchronized. So we used the tau setting available in the relays, and in this case we calculated a kappa term equal to about 13 seconds. It's a very huge time synchronization error. I mean, the local and remote relays are completely unsynchronized. In this case, since we do not know the real time synchronization error, we had to use the Bewley diagram to validate the proposed solution. And in this case, after the synchronization procedure, we could see that the traveling waves patterns match. I mean, when we put here the remote measurements, we can see that the time instants coincide and they match what we are expecting to see. So it demonstrates that the proposed solution indeed was capable of synchronizing local and remote records. Thus, as conclusions, we can say that a reliable and accurate alternative transmission line time synchronization method was developed. It is adaptive to uncertainties in line travel time settings, and it overcomes the need for energization tests. Regarding the performance demonstration, we considered simulated and real case. In the best case, time synchronization errors in the order of fractions of microseconds were obtained, and in the worst case, errors in the order of few microseconds were obtained. These results are very promising in our opinion, and even in the case in which we do not have the control of time synchronization errors, in which originally unsynchronized records were analyzed, the Bewley diagram confirmed that the solution is reliable. So we can conclude that the method is a good alternative for record alignment procedures when traditional solutions are unavailable, like GPS and communication channels. That's it. I would like to thank you for your attention, and I invite you to follow us in our channels. Thank you.